Hey guys, I want to work through some of the section 3.3 notes with you today. So if you remember, again, we're working on the chapter that's telling us all the things that we can do with the derivatives that we learned about in the last chapter. So we talked about the how to find extrema on a closed interval for a continuous function. Then we looked at Rawls' theorem and mean value theorem that tell us that the average rate of change over an interval, over a closed interval, of a function that is continuous and differentiable, there will be a point in there. So Rawls' theorem says if we've got two values that are the same, a and b, and we've got a continuous differentiable function on that interval, the average rate of change on that interval is 0, and it tells us that there's going to be at least one point in there where the instantaneous rate of change will also be 0. Right? In this example, there's 2. And then for the mean value theorem, again, we've got to have a continuous function on a closed interval that's also differentiable on the open interval. So it says that if the endpoints are not equal in value, but we still have some sort of nice function in there, tells us that the average rate of change between the beginning and the end point will be matched by some other point's instantaneous rate of change in that same interval. All right, so the next thing that this chapter is going to tell us what we can do with derivatives is to find intervals where the function is increasing and decreasing. We'll do that in different ways, and one of those ways will be the first derivative test. All right. So again, the beginning part is going to be a lot of definitions and theorems, but we'll look at some examples. So it says if a function f is increasing on an interval I, if for any two numbers x1 and x2 in the interval, where x1 is less than x2, that means that f of x1 is less than f of x2. So again, let's just sketch something here. So let's say we've got x1 less than x2. If f of x1 is less than f of x2, then that means that the function in this interval is increasing. All right? So again, it shouldn't be surprising to see that, but this is just the very mathy way to write it. All right, then we have a function f is decreasing on an interval I if for any two numbers x1 and x2 in the interval, if x1 is greater than x2, then f of x1 is greater than f of x2. Sorry, that is a typo. This should be x1 is less than x2. I'll change that on the handout I send you. So again, if we're reading left to right here for our intervals, all right, x1, x2, if any 2 points in some interval I, doesn't matter what the points are, if I can always say that f of x1 is greater than f of x2, then it's decreasing in that interval. All right, so for some interval I, if I pick any 2 points, not just if I can find a pair of points where that's true, for any 2 points in that interval, if x1 is less than x2, but f of x1 is greater than f of x2, it means it's decreasing. Okay, a function is increasing if, as it moves from left to right, its graph moves up. It's decreasing if its graph moves down. Right, so as we read from left to right, this is stuff that we've already talked about in other classes, except it was always with linear functions, but now we're saying this is true for anything. As we read from left to right, if the graph moves up, it's increasing. As we read from left to right, if the graph moves down, it's decreasing. A positive derivative, again, remember the derivative means slope, so if it's a positive derivative, a positive slope implies that the function is increasing, because if the slope is positive, it's increasing. A negative derivative implies that the function is decreasing. A zero derivative on an entire interval implies that a function is constant. Again, we've seen that before with just constant functions, right? So let's say we've got y equals 5. We take the derivative of that, y prime would be 0. Right? So if it's 0 on the entire interval, the function must be a constant on that interval. All right, so how to test for increasing and decreasing functions. So we've got f is a function that's continuous on the closed interval and differentiable on the open interval. So these are the conditions that were required for Rawls' theorem, mean value theorem. Right, if the derivative is greater than 0 for all x in that interval, then f is increasing on the closed interval. Right? If the derivative is less than 0 for all x in the open interval, then f is decreasing on AB, closed AB, and if the derivative of the derivative of f is 0 for all x in that interval, then it's constant. All right, so it's just taking this paragraph and writing it as a theorem. All right, so then we've got an example here. So find the open intervals on which this function x cubed minus 3/2 x squared is increasing or decreasing. So what we need to do is we need to use this theorem 3.5 and find out where the function's increasing, decreasing, and 0, but we're going to do that first by checking to make sure that the conditions are met, and then we're going to find out what the derivative is. All right, so let's take this function and we're going to say f prime of x. Well, first of all, we want to make sure the conditions are met. So before we do that, we need to make sure it's continuous everywhere. Since they didn't give us an interval, we just have to do it for every point here. So it is continuous everywhere because it's a polynomial. We also have to make sure that it is differentiable everywhere. Right? Again, polynomials, all polynomials, when we take the derivative, they are differentiable. So yes, it is differentiable everywhere. All right, so we've checked the requirements are met. So then we're going to take the derivative. So f prime of x equals, this is going to be 3x squared minus 3x. All right, what we need to do is we need to find out when it is 0, because anytime the derivative is 0, that's where it's going to change from potentially being, well, it's going to change from being either positive to negative, negative to positive. There are in some cases where it would be positive to positive or negative to negative, but 0, whenever it's 0, that marks a change potentially. So we're going to find out where this derivative is 0. So we've got 3x squared minus 3x equals 0. We'll factor out a 3x, so we get x minus 1 equals 0. And then that says that x equals 0 or x equals 1. Right? So those are the two spots where something interesting is going to happen. All right? So in fact, if we were to make a sketch of this, all right, if I plug in 0, I get 0. If I plug in 1, I get 1 minus 1.5, so that's going to be negative 1/2 here at 1. So let's say this is 1. All right. If I were to find the zeros of this function, just to figure out where it crosses over the x-axis, if I said x cubed minus 3/2 x squared equals 0, then I would end up factoring out that x squared. I would get x minus 3/2. So in addition to the 0, which I already know, I would get at 1.5. There's also a spot where it crosses over. All right, so let's just kind of figure out what's going on here by using this information. All right, so the interval that I'm going to set up is one that goes from negative infinity to 0, because again, if we're thinking about this on a number line, something interesting happens at 0 from a derivative perspective, and something interesting happens at 1 from a derivative perspective. So that means that everything to the left of 0 should just be exactly the same, because it doesn't ever turn from positive to negative or negative to positive. So this is our first interval. Our second interval is something is going to be consistently happening here, either all positive or all negative, because it can only switch by crossing through 0 since this is a continuous function. So we're going to look next on the interval between 0 and 1. And then again, the third interval that these 2 points split the number line into is 1 to infinity. Okay, so again, I take those 2 points that we found when we took the derivative and set it equal to 0, and I make them the endpoints of intervals. So negative infinity to 0, 0 to 1, 1 to infinity. If we had been given a closed interval here, like let's say negative 5 to 5, we would use those as the other endpoints of the interval, here and here. But since they didn't give it to us, we're just doing it out to infinity. Okay. So then what we're going to do is we're going to pick a representative from that set, because there is, again, there's no point where it crosses, where the derivative is 0 in here, so it's either going to be all positive or all negative. So let's just pick a test value, and I'll pick x equals -1, let's say. In here, we need to pick a test value, so let's go with x equals 1/2. And in here, we need to pick a test value, so let's say we pick x equals 2. And then we want to find out what the sign of the derivative is, because again, that tells us the slope. All right, so if I put -1 into the derivative, I'm going to pick here to do it, as opposed to here. This is saying 3 times -1, that is going to be negative. And then -1 minus -1 is going to be -2. So negative times negative, that means this must be positive. Then I'll do the same thing in here. I'll pick 1/2. 3 times 1/2 is positive. 1/2 minus 1 is negative. So positive times negative, this is going to be negative. And then at 2, 3 times 2 is positive. 2 minus 1 is positive. Positive times positive is positive. Again, notice I didn't care about the number. I just cared about the sign there. All right, and the conclusion then that we would make, since the slope or the derivative is positive, it's going to be increasing on this interval. Since the slope or the derivative is negative in this interval, it's going to be decreasing here. And since the slope or the derivative is positive here, it's going to be increasing again. And again, with the little bit of information that I have, just with these 3 points and this information, I can make a rough sketch of this graph. Again, I won't know the actual values for some of these other points, but I can say it's increasing here, it's decreasing to this point right here, and then it's increasing beyond that. So our function should look something like that. Okay, next page. All right, so this is just going to summarize the steps that we went through in the last problem there. So if f is continuous on the interval, the open interval AB, to find the open intervals on which f is increasing or decreasing, use these steps. And again, this is exactly what we did. Find the critical numbers in that interval. Right, again, critical numbers, remember those are where the derivative is 0, f prime equals 0, or it's undefined. Use these to determine the test intervals. Recall that, I didn't need to write that because it was there already. Its derivative is 0 or it's not differentiable at that point. All right, determine the sign of f prime at one test point value or one test point in each of the intervals. Use theorem 3.5 to determine whether f is increasing or decreasing on that interval. And then that will tell us where the function is increasing or decreasing. These guidelines are also valid if the interval is replaced by an interval of the form negative infinity to b, a to infinity, or negative infinity to infinity. That's the one that we had in the last example. All right, hopefully that's good. All right, let's take one look at this next set of definitions here. So it's saying a function is strictly monotonic on an interval if it is either increasing on the interval, on the entire interval, or decreasing on the entire interval. All right, so I'm going to draw a strictly monotonic function here. And that might look like this. All right. So it's always increasing. You could do one that was always decreasing, but it just on a given interval, and again, I'm doing mine as one that's from negative infinity to positive infinity, but you could also have one where on the interval a, b, it's just strictly increasing in that section, all right? It might do something outside of that interval, but inside the interval, it's strictly monotonic. All right, it is not strictly monotonic if it does something otherwise. So again, it might say that we go increasing to here, and then for some reason it flattens out here, and then it goes up. All right, so it is doing a lot of increasing. It's never decreasing, but it's not always increasing because of this section right here. So this would be when you do not have a strictly monotonic function. Okay. Let's read through this, and then I think I need to switch videos. Let C be a critical number of a function that is continuous on an open interval I, which contains C. Okay, so again, it's saying that it is nicely behaved on an open interval that contains some point C. If f is differentiable on the interval, again, that means that there are no sharp turns. There's no place where the derivative, the slope of the tangent line is going to be vertical, except possibly at C. Then f of c can be classified as follows, right? If f prime, the derivative, changes from negative to positive at c, then f has a relative minimum at the point c, f of c. Again, what that's saying here is at c, right? If it goes from positive to negative, if it goes from negative to positive, that means it's decreasing and then it's increasing. That tells us that it has a minimum at that point. If it goes from positive to negative, again, what that would look like is if this is C right here, and that's f of C, if it goes positive to negative, that means it has a relative max at that point. If f prime is positive on both sides of C or negative on both sides of C, then f of C is neither a relative max nor relative min. That does happen sometimes when we've got something like this, where it does a very, very flat gradual turn. Not so sharp as this, where it just kind of, does a little bit of a, bevel there. This where it really flattens out in there, not so that it's zero constantly, but just that it does that. That would be a case where it's positive on both sides, all right? And the derivative is still zero there because the slope of the tangent line is zero, right? That is not a max or a min, but it will show up as a critical value. All right. Next page. Actually, so really what we're going to do is we're just draw those three pictures here. All right, so the relative min looked like this, where it goes, here's C, let's say here's f of C, and the slope was negative here, so decreasing, and then here it turned to positive after. So that's where it looks like a relative min. And again here, where here's C and f of C, positive, negative, that's how we get a relative max. And here, neither relative min nor a relative max, where let's say, this is, I don't have to do it right on the axis, so let's say that this is C and this is f of C, and it goes like this, where the tangent line there has a slope of 0. Okay, I'm going to come back in a second and we'll do example 2 and then be done. So let's take a look at this example, example 2. So find the relative extrema of the function f of x equals 1/2 x minus sine x in the interval 0 to 2 pi. All right, so again, the relative extrema would be the relative max or relative min in this interval of this function. All right, so this is what we were just talking about. We're going to look for the critical values. We're going to set up a table here and pick a test point and find out where it's positive and negative. Okay, so first let's make sure that the conditions are met. right? So we've got here a polynomial function, which is continuous everywhere. We've got this sine function, which is continuous everywhere, so their difference is going to be continuous everywhere, right? So they tell us specifically between 0 and 2 pi, but we can say even more than that, it's continuous everywhere, all right? So we'll say the function is continuous on negative infinity to infinity. All right, so then we would like to know if it is differentiable everywhere, and that is also the derivative of sine is cosine, which is differentiable everywhere. The derivative of a polynomial function is continuous everywhere, so it is differentiable everywhere. But we'll say specifically in 0 to 2 pi, this, and specifically 0 to 2 pi. Okay, so again, if you're looking at your list of guidelines on the previous page, we had to make sure that it met the conditions, but now we're trying to find the critical numbers. And the critical numbers come from taking the derivative of the function. So we've got f prime of x equals 1/2 minus cosine x. All right, so we need to figure out where this function is, where the derivative is 0 or undefined. Again, it's not going to be undefined anywhere because cosine is continuous and that's just a constant. So really we're just looking for where is f prime equal to 0. So we're going to take 1/2 minus cosine x and we're going to set it equal to 0. We're going to bring the cosine over the other side, so we've got cosine x equals 1/2. Right, so then we would say where in 0 to 2 pi is our function equal to 1/2. Right, so cosine is 1/2 at 60-degree angles, or pi over 3. So in quadrant 1, that's going to be, quadrant 1, that is going to be x is equal to pi over 3. And then, again, if you remember our mnemonic, all students take calculus, it's in the first and the fourth quadrant. So in quadrant 4, that's going to happen when x equals, again, this is 6 pi over 3, so it's just 1 less than that, so it's at 5 pi over 3. So these would be the two spots where cosine is equal to 1/2. So then, sadly, the box is on the next page, so you're going to have to flip. But let's just make a quick sketch of this. All right, this function will be 0 at 0. If we plug in 0 here, we're going to get 0, and sine of 0 is 0. All right, I'm going to put a hollow dot there because we have the open interval right here. We also know that at pi over 3, so let me sketch this out. So this is 1 pi over 3, 2 pi over 3, 3 pi over 3, which we just call pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, which we just call 2 pi. All right, if we were to plug in 2 pi here, sine of 2 pi is 0 again, but if we plug in 2 pi here, we get just pi. All right, so if I count this as 1, 2, 3, 4, 2 pi, or I'm sorry, pi would be somewhere around here. All right, we also know that it's going to be 0 in addition to at 0. It's going to be 0 at 2 pi over 3. Why am I saying that? Sine of 2 pi over 3 sine of 2 pi over 3 is root 3 over 2. I'm not sure why I'm saying that. I have it marked as 0 on my graph. Whoops, and this is not pi over 3. This is pi. It's 3 pi over 3. This is 1 pi over 3, 2 pi over 3, 3 pi over 3. I have it marked here that it's 0. Let's think about that. So sine of 2 pi over 3 is root 3 over 2. Maybe it's not exactly there. It might be I just sketched it because it looks like it's close to there, but I have it marked as right there. Okay, so let's go through with, we'll leave that for just a second, and let's come back after we fill in the table on the next page. All right, so again, I'm going to have both of these available to us because we have to make sure that we set up the proper intervals. So the endpoints of our intervals are 0 and 2 pi. So we have to make those the outer limits there. Again, in our last example, it was just negative infinity and positive infinity. Our first stopping point is going to be at pi over 3. And then it's got to be between pi over 3 and 5 pi over 3. And then 5 pi over 3 and 2 pi. All right, so we have to pick a test value between 0 and pi over 3. Again, this is a 60-degree angle, so you could try pi over 6, which is 30, pi over 4, which is 45. I'm going to choose pi over 4. In this interval between pi over 3 and 5 pi over 3, there's a lot of nice whole pi values. In fact, I'm going to choose x equals pi. You could also choose 3 pi over 2. And then here, same thing. There's got to be a pi over 4 multiple in there. And in this particular case, it's a 7 pi over 4. If you're not sure about that, just draw yourself a number line like this and put them on there. So 0, pi over 3, and 5 pi over 3. Actually, if you do it on our graph here, that might help. So here's pi over 3. And then this is 5 pi over 3. And you can figure out values that are between there. Right? So between here would have to be pi over 6 or pi over 4. And then between here, again, a pi over 6 or a pi over 4. And then in between here, that's the largest of the intervals, we've got the nice pi. Okay. Then we take and find the sine of f prime. So again, here is our f prime right here. 1/2 minus cosine x. I'm going to put it at the top of this page now. We'll scooch this out of the way. F prime of x equals 1/2 minus cosine x. Sorry, the washing machine's going in the background. I hope it's not too noisy. All right, so we'll put in pi over 4. So this is 1/2. I'm just going to do scrap work up here. 1/2 minus cosine of pi over 4 is root 2 over 2. All right, clearly this is bigger because root 2 is bigger than 1. So it's 1/2 minus something bigger than 1/2. So this is going to be negative. All right, if we put in pi, we've got 1/2 minus cosine of pi. Hopefully remember cosine of pi is -1, so 1/2 minus -1, this is going to be positive. And then we put in 7 pi over 4, so 1/2 minus cosine of 7 pi over 4. Again, pi over 4s give us a root 2 over 2. 7 pi over 4 is in the fourth quadrant, and cosine's positive there, so this is going to be 1/2 minus a root 2 over 2 again. So this is also negative, just like the first one. All right, our conclusion. Since the derivative is negative on this interval, it's decreasing. Since it's positive here, it's increasing. Since it's negative here, it's decreasing. All right, so we need to actually find some values here. Let's go back to our graph. Actually, we don't even need to go back to our graph because we know what to do here. Sorry for the lack of space, but I'm going to put in those values in our table. Again, we're not going to count 0 because it's not, well, we could put it in and find out if it makes a max or not. So our x values, our f of x values, if we put in 0 just to see what happens, not that we're actually allowed to include it, pi over 3, and then 5 pi over 3, and then 2 pi. All right, again, sorry, you're going to have to do this elsewhere because otherwise it's going to run into here. At 0, our original function, which was f of x equals 1/2 x minus sine x, at 0 it was 0. At pi over 3, All right, that is 1/2 times pi over 3 minus sine of pi over 3, which is root 3 over 2. We end up with something really kind of nasty here. We get pi over 6 minus root 3 over 2. At 5 pi over 3, we're going to get something very similar. It's going to end up being 5 pi over 6 minus, and then 5 pi, sine of 5 pi over 3 is minus a negative because it's negative there, so it's going to be plus, and then that's root 3 over 2. And then at 2 pi, we're going to end up getting just pi. All right, we plug in 2 pi for x here, the 2's will cancel, so we're just left with a pi, and sine of 2 pi is 0. Okay, so then we end up, we need to find what the values there are. Pull out my handy dandy calculator. So pi over 6, sorry, I don't have the decimal values. I can just say where it's happening, but actually, I'm not even going to do that. Well, yes, I will, just since I started at minus second root 3 divided by 2. I've got negative 0.34. And then 5 pi over 6 plus root 3 over 2. Is 3.48. And here this is about 3.14. All right, I don't actually need to do that because I can tell from here, it'll help us just when we go to graph. I can tell from here that since this is decreasing and then increasing, at pi over 3 there is a minimum. All right, where the minimum is, I can't tell unless I do this. But the x value of the minimum is this, right? Here we go from increasing to decreasing. That tells us that at this point there has to be a max. So let's go in and sketch this a little bit more accurately. We have this so far. We know from our table that from here to here it's decreasing, and I just found out that it's at negative 1/3 roughly. So we're going to put in the value right here. And then it tells us that at 5 pi over 3, it's up at about 3.5. All right, so that's right here, let's say. This was a little too high. All right, and it's increasing, so it's got to look something like this. Decreasing, increasing, decreasing. All right, so our function's going to look something like that. Again, that's probably not exactly 2 pi over 3, but it's somewhere close. All right, so again, you don't have to skip this. You don't have to do this part. This table enough tells us where the relative max and the relative min are, but it will help us sketch the graph if we know what the y values are. But again, it didn't ask us to do that, so technically you don't need to, but I just wanted to be able to sketch the graph so that you could see that yes, we're actually correct in what we said. Right, so these are the 3 things that are going to help us decide. The min is going to occur here, and the max is going to occur here. All right, so max at x equals 5 pi over 3, min at x equals pi over 3. Okay, that's it.